Hello everyone, good morning. Welcome to the ChromeOS Graphics 101 talk. My name is David and I have been working on various components in the ChromeOS graphics stack over the last 7 years. And this talk will give you an overview of the components that make up the ChromeOS graphics stack, and it will give you an idea how those components communicate in order to take content from, example, a web page or an application and present that on your display. ChromeOS graphics stack is built on the DRM API in the Linux kernel, and display compositing is done by Chrome. DRM here refers to Direct Rendering Manager. It's a kernel API and a subsystem within the Linux kernel for graphics. I'll be using that term a number of times throughout the presentation, and if you work on ChromeOS graphics, you'll see that in a lot of the code and a lot of the documentation. So it's important to know what that refers to, and it's this graphic subsystem in the kernel and not some other version of DRM. Let's start by taking a look at a few screenshots from ChromeOS. This first screenshot has a really simple web page. It's just a simple rectangle. You won't see it in the screenshot, but it's actually animating the color of the rectangle, but very basic web page. This next screenshot, the user is actually it's in the process of closing the browser window. I managed to capture this halfway through the animation that is taking place on ChromeOS when you close a window. So you can see that the window is a little bit smaller and it's half translucent. That's the ChromeOS UI doing that effect as a result of you closing the window. Then you have the Play Store running. And lastly, you have a Linux application. In this case, it's editor, and we're editing some code. So there's quite a few different things happening here. And in order to do all these things efficiently, it requires a fairly complicated graphics stack on ChromeOS. This is an overview of what that graphics stack looks like. At the bottom, you'll have the hardware, the graphics hardware. And further up the stack, you have a number of layers further away from the hardware. And at the top, you'll have the applications. I'm going to go through and describe some of these components in the next couple of slides. I apologize for being fairly brief. I want to get to the second part of my presentation, which instead will describe how these components fit together and how content flows through the system. So if you want more details on some of these, I can provide you with the resources after the talk. So closest to the hardware, you'll find DRM. This is the subsystem in the Linux kernel that allows us to control the display hardware, and it allows us to submit commands to the graphics hardware for rendering. So beyond the basics, it provides a few features that are critical to ChromeOS these days. So I wanted to point those out because you'll see those mentioned throughout this talk, and you'll see it in other parts of documentation throughout ChromeOS. The first thing is atomic display updates. This is something that's critical for using hardware overlays. Hardware overlays is a mechanism for more efficiently presenting content on a screen. It allows us to bypass compositing using the EPU and scan out buffers directly. And that's important for performance and for power usage, especially on lower-end devices. Atomic display updates, that's the feature that allows us to take advantage of that, because we can switch hardware overlays on and off without causing rendering artifacts. The second thing that's very important to ChromeOS is buffer sharing, or the sharing of graphics buffers between different processes and different parts of the system. Now that we're running both Android apps and Linux applications, we need an efficient mechanism to share graphics buffers from one part of the system with another. And this API that DRM provides gives us that. MiniGBM sits on top of DRM. That's our graphic buffer allocation library. It's maintained by the ChromeOS graphics team. If you're familiar with Android, you might know of Gralloc. MiniGBM is our version of Gralloc. It allows you to allocate buffers for graphics, and it hides all the device-specific details from you. That would be padding or alignment of the buffers. It has support for importing and exporting buffers, and it has some more advanced features that we use on some devices for tiled buffers and frame buffer compression. Another component is, of course, the graphics drivers, the GPU drivers, and that's how we do accelerated rendering. ChromeOS graphics drivers are not very different from a normal Linux graphics driver. There's a kernel space part to it that's part of DRM, and there's a user space part. I guess the only difference compared to maybe normal Linux laptop is that we require a comprehensive set of tests to pass for the driver to be good enough to use on a ChromeOS device. Chrome, the browser, will access the user space part of the driver through a specific process we call the EP process. This provides a few benefits. It's good for two reasons. It gives us the ability to isolate that process, sandbox it, which is good for security. It's also good for stability, because it means that if we have issues in the driver that causes that process to crash, it doesn't mean that we take down the whole browser. We can actually restart the GPU process, and you never noticed. You'll still be using your web page, and everything will work just fine. Android, on the other hand, have direct access to the user space part of the driver in the application. That gives them a little bit improved performance. That could change in the future, but that's how it works today. Linux apps are still lacking the support for accelerated rendering, but our current plan is to use Virgil for this, but that's still ongoing work. Chrome is, as I'm sure you know, a multi-platform browser, and it supports various platforms like Windows, Mac, and Linux. The ChromeOS platform is called OS on DRM. This is where all the details of how DRM works is hidden from the generic code in Chrome. As part of this, we implement a number of primitives in Chrome on top of DRM and expose them to Chrome. These type of primitives is how we can still allow Chrome as in platform-independent code to take advantage of a lot of these features that DRM gives us, hardware overlays being an example of that. Then we're going to move on to the Chrome compositor. I think this is a talk by itself, and I tried to capture some of this in one slide. The Chrome compositor was originally built to composite web pages. So CSS elements and handle animations of that, bring in WebGL and how to combine that with the rest of the content. On ChromeOS, we use that same compositor code to composite the ChromeOS UI. So the same code, the same logic that will handle your video inside the page or your div inside the page that's animating, that's the same logic that will animate a window on ChromeOS. The compositor is split up into different components, different instances. You'll have one part of the compositor running inside each tab for a web page. And then you'll have another instance for the UI on ChromeOS. And they actually talk to a parent compositor called the display compositor. And the display compositor is the one that produces does the final compositing that can be sent to the display. Some of these instances will do rasterization, so they'll take content, some description of the web page, and they will produce pixels from it. The renderer compositor, for example, does that for the web page. And then we have a number of effects that the compositor implements. We're currently using your standard GLES to implement a lot of those effects. That might be Vulkan one day, but it's still GLES today. And there's support for hardware overlays as part of the compositor. The ChromeOS UI is implemented on top of the Chrome compositor. It's just another client of the Chrome compositor. And it uses some of the effects that the compositor provides for animating windows and drawing drop shadows and similar things. Exosphere is a Chrome component that allows clients outside of Chrome to integrate with the display system inside of Chrome. And the example for this is Android applications and the Android framework, how it can take content produced by Android and integrate that with the Chrome UI and the Chrome display system. And same thing works for Linux applications. And what this really does is it implements the standard Wayland protocol, which effectively makes ChromeOS version of Chrome a Wayland compositor. Wayland, if you're not familiar with it, is the compositor API that is being used on Linux that is supposed to replace X11. R++ is how we can get Android applications to be presented efficiently on ChromeOS. We have a graphic implementation on top of mini GBM, so we allocate graphics buffers that can be shared with Chrome that way. We're using our drivers that we have for ChromeOS already for rendering inside of Android. And we have a special implementation of Hardware Composer, which on a normal Android system is what drives the display. In our case, our Hardware Composer implementation, instead of talking directly to the display, it's actually going to talk to the Exosphere component inside of Chrome, which will then talk to the display compositor and integrate the content with the rest of Chrome. And the last piece is Crostini, which is how we run Linux applications. It's very similar to how Android applications work. Cross VM is instead allocating these graphics buffer in the Crostini case. Instead of Surface Slinger and Hardware Composer, we have a different proxy compositor inside of the Linux container called Sommelier that will actually turn content from Linux applications into something we can share with Chrome. But other than that, it's very similar to how Android applications work. So those were the components. Now we're going to look at how these components work together and how content will flow through the system before making it to the screen. In the general case, we'll have a web page, an app, or some part of the UI that is changing. And that results in that change propagating to the Chrome compositor. The Chrome compositor then generates something new to be displayed, and that goes to the Chrome platform, which is Ozone DRM in this case, and that talks to the kernel, and then the kernel will actually talk to the display hardware to get something to show up on the screen. Let's take a more specific example. First, we'll do a web page, so some HTML content and how that makes it to the screen. So first, the example we have here is just like my screenshot, a simple rectangle that's animating. It triggers Blink to do paint, and that causes Blink to generate a new display item. So we get a change to a display list so that represents the content, and that will make it to the compositor instance that's inside the renderer process. The renderer compositor will, as a result of that change to the display item, have to re-rasterize part of the page. So this triggers rasterization, and the rasterization will actually take the description of content and it will turn that into pixels in some buffer or texture that can be shared with a display compositor. We are not only on ChromeOS, on all platforms we use Skia for rasterization. Most ChromeOS devices these days use accelerated rasterization, so they will use the GPU for rasterizing the content. Some will still not do that, but they're still relatively efficient because they can make use of some of these lower level graphics primitives for eliminating some copies and making the transfer of the data into graphics buffer very efficient. Once that's done, it will produce a frame, we'll submit it to the display compositor. The display compositor, it will allocate an actual buffer that can be sent to the display for being scanned out. So it allocates the buffer, it takes the content from all the tabs, all the web pages, and it will use GLES to produce this final frame. Once that's done, it will give that frame to Ozone DRM so it can be presented. So Ozone DRM takes that scan-out buffer, it uses the kernel API to schedule it for presentation. Eventually, it will find out when an old buffer is not presented anymore, and it can start reusing buffers. But the kernel API, once it receives the buffer, it will have to wait for some potential set of rendering commands to complete before the buffer can be actually given to the display. Once that happens, it will wait for a certain event that allows it to switch the previous buffer with a new buffer without causing any noticeable artifacts. This is usually called a vsync event. And then once that happens, it will switch to the buffer and it will notify Ozone DRM that it did. So let's just go through a summary of that. First, there we go. First, the change in the document triggers paint in Blink, and then that paint triggers rasterization in the renderer compositor. Rasterization generates a new display compositor frame. The display compositor produces a new scan-out buffer, and that's passed to Ozone DRM. They will schedule it for scan-out. The kernel driver will tell the hardware to start scanning out from the buffer, and then the display hardware will eventually turn that into, turn those pixels in that buffer into light. The next example I wanted to go through is the same thing, but in this case, it's the ChromeOS UI that's causing something to change on screen. In this example, we have the ChromeOS UI animating a window as a result of you closing it. So it's animating the opacity from 1 to 0. This doesn't require us to do any rasterization. What we can do for that is we just change an opacity property on the layer. So the ChromeOS UI will do that, and the UI compositor will not do any rasterization. It will just change some property and submit it to the display compositor. The display compositor now does pretty much the same thing it did in the past. It's like it needs to implement that opacity effect. This particular effect requires you to allocate a temporary texture. So it does that, and it applies the effect and generates the scan-out buffer. And then the mechanism is basically the same after that. After the UI generated the change to the layer, we produced a new display compositor effect. The display compositor did something a little bit differently here to implement the effect, but it produced a scan-out buffer, and then things are the same all the way to the actual display. One of the last examples I want to go through is the Android app, because here things changed a little bit. This example, we're using the Play Store. So user is, for example, scrolling content in the Play Store. On the Android side, that will use the accelerated canvas API, and that API will use the Alias driver to produce a new content, and it will pass it to Surface Flinger. Surface Flinger will talk to our implementation of Hardware Composer, and instead of talking directly to the display, it will create a frame and submit it to Chrome, where it will integrate with the rest of the ChromeOS UI. On the Chrome side, Exosphere receives this frame. It happens that in the Android application case, that frame it receives, that buffer has been allocated in such a way that it actually is a good candidate to be used with a hardware overlay. So Exosphere will mark this as a potential hardware overlay candidate, and then submit a frame containing that to the display compositor. And the display compositor, in this case, will do something very similar to what it did for the web page and for the UI, except it will notice that this is a hardware overlay candidate, and as a result, it will skip all the compositing it did in the past using the Alias and the GPU. It will just bypass that and take this buffer and set it up for scan out directly. So that saves us a lot of time producing that big scan out buffer that represents the whole display. In this case, we can take the application buffer directly and pass that on to Ozone DRM. So the summary is you scroll some content, it produces a new frame on the Android side, it's being sent over to Chrome, and we produce a display compositor frame. The display compositor determines that you can use a hardware overlay, and instead of doing any compositing, it's just going to pass that buffer directly to Ozone DRM, where the kernel will tell the the display hardware to just scan out from this buffer directly. And that will eventually turn into light. Linux application is very similar, so I can quickly go over that. In this case, it was a text editor called dedit, and you have a toolkit inside of Linux that actually renders to shared memory. That shared memory is being passed to our proxy compositor inside the Linux container. That proxy compositor called Sommelier will take that frame and it will turn that into something that can be shared with Chrome. In this case, it will be a buffer allocated using DRM and shared with DMA that can be used as a hardware overlay. And that after doing that copy of the shared memory into that buffer, it gets submitted to Chrome. And now Exosphere does practically exactly the same thing it did for the Android app. It will produce another display compositor frame with a buffer marked as a hardware overlay candidate. And then the display compositor will process that in exactly the same way and avoid any additional compositing, but instead passing the buffer directly to the display hardware. So quick summary, you're typing something in the editor, and you get a frame, and you schedule that, and eventually get some light on the screen. And I think we're going to wrap it up there. There's some other additional fancy features that ChromeOS provide, but I won't go into details for that. I think we should move on to questions. Okay, the question is if mini-GBM is used anywhere else than ChromeOS. Not that I'm aware of today. I've used it for some experiments inside of Crostini, but I'm not aware of any other use case of it. Another one from the Dory, or live question.
Yeah, I just had a question. On that big stack of layers, is the KRM to the display hardware the only time it's synchronized to 60 hertz, or are there multiple stages along the way?
Yeah, so I, as I was limited on time, I didn't go into any details on how scheduling is handled, but there's a number of systems in place for how to decide when to produce new frames, and how, if you're producing them too fast, how that back pressure comes up through the system, and all these mechanisms will be to some degree aware of the refresh rate of the display and so on, to be able to not go too fast. Did that answer the question?
Yeah.
Can you answer one more?
Yeah. So the question is if we can eliminate Ozone DRM and talk directly to the kernel, the answer to that is yes, you could do that. Ozone DRM is sort of this meta platform that supports a few other things than just DRM. It would be possible to create a Linux platform that talks directly to the kernel, if that turns out to be beneficial in the future.
Hi, I have a question. We come up with a few Chromebooks every year. They have different CPUs. So is there a auto test that we can use to benchmark the graphics performance of one Chromebook against another?
Yeah, I think there's probably a bunch of different benchmarks you could use. I think it depends on what you're interested in measuring, I think.
So is there an auto test, or you are saying standard apps, like the graphic apps on the Play Store? What do you mean?
The way for measuring the performance?
Yes.
I think there's a lot of different mechanisms for performance measurements throughout Chrome. I'm probably not even aware of all of them. Some of them probably run standard applications. Chrome has a way of running, automating the web pages and run the top 20 web pages, for example, and get performance number out of that as well. So we have performance tests in pretty much every part of the platform.
And another question I have is when we come up with a new CPU that may have a new GPU or new graphics hardware, so typically in the stack, what parts need to be changed? Is it only the kernel driver, or is it further up in the stack also?
Typically, it's only the kernel driver and that user space driver that I also mentioned. So the kernel side part of DRM most certainly needs to be updated. And then that user space part of the driver will need an update as well. But most of the time, the rest of the graphics stack will not need to be changed, unless this type of hardware is introducing some new feature that we want to take advantage of, and we need to change things at a higher level.
Take one final question.
Yeah.
Is there a particular component in the graphics stack, historically, if you look at the crash logs, particular component that's particularly sensitive, or you see that particular component being most sensitive to crashes?
The graphics drivers in general crashes a lot. That's part of the reason why we have that model in Chrome, where we have a separate process that talks to the graphics driver. That's good to have on ChromeOS, because we will have a lot of crashes in the driver, or will hang, or similar things. It's even more important on other platforms where we have less control over the drivers. On ChromeOS, at least, we have some quality control over the drivers, but imagine running Chrome on Windows, you don't have that, so it becomes even more important. But I'd say that, yeah, that's an area that we probably have the most crashes in the drivers, because it's complicated and it's optimized for being fast, maybe more so than being perfectly stable.
Thank you very much.
Thank you.